quasi tutto la maglietta e la stampa.
Diciamo che si sta tanto buttando sulla post-creazione e quindi è un po' buttato peccato secondo me non è capito, però
se vuoi scrivo, mi è mancato.
diglielo infatti.
Quando comincia? E adesso c'è sta Francesco che sta a fare una decisione. Sì. Eccolo qua.
Allora, io mi sento qui però perché tanto lo devo...
Sì, il privilegio Gilli non ce l'hai, quindi porti anche in giro il microfono.
Ciao, tutto bene?
Sì, bene, grazie.
Vuoi il segno quando mancano solo 2 minuti o ne vuoi uno prima? O... 3 minuti, va bene, facciamo 3 uguali. C'hai 12 più 3. E poi mi alzo quando...
Mi fai brutto.
Ma ce le tutte le presentazioni?
Sì.
Luca l'aveva mandata io mail.
Sì, ce l'ho.
Ah, io ho anche i talk alla fine dei ragazzi. Quello lo sanno loro l'ordine?
Glielo dico io, ora recupero il chat. Guardo da sotto. La metti da qui, no, di lì, non si sa. Prendo il punto, vai. Vai, lascia fare.
Ok, so take your seats, fasten your seatbelt, emergency, no, that's... Forza Roma. No, I didn't say this, eh? I thought continuously since yesterday. Ma scusate. You need to pay attention. No, che foto devo... Se poi possiamo mettere... Avresti dovuto aggiungere la slide. Questo è vero. Ok, almost ready to start. Sì. Ok, let's go. Let's start with this session with Tullia about how to build the early monster black holes, put jets in your toolbox.
Hello, everyone. I'm very, very happy to be here and see all of you in person, and quite many people after the social dinner. Well done, guys. So today I'm going to talk about early monster black holes, and I have to explain in what sense early monsters. We are the high redshift section, let's say. So early, it's because we are going at very, very high redshift, larger than 4, and we will see larger than 5. Monsters, because they are monstrously massive, and all those black holes that we are of which we are measuring the mass at such high redshift have masses of more than 10 to the 9 solar masses, almost all. We already seen a few bits, some talks earlier. They are all quasars. I will focus on quasars, so very broad emission lines, bright big blue bumps that suggest that they are quite highly accreting, at least 10% of the Eddington ratio. And something that will be focusing on will be the radio loudness that is generally associated with the jet to nucleus ratio. If source is very radio loud, you all know that we expect that the jet is very bright and it's present. So we already saw, but this is a different version, that there are a few radio loud sources at very high redshift, and the fraction of radio loud sources at redshift larger than 5 apparently is consistent with what we see in the local universe, about 10% of the sources. But we have a problem, because with the radio all sky catalogs, we are already reaching the sensitivity limit. Okay, so maybe we are missing something, we are not very sure. So in the past we have used a different tracer for study the number of jetted sources at very high redshift, that is blazars. Blazars are very useful because we know that they have their jet pointing towards us, and so we can infer for each blazar we observe the presence of hundreds of analogous sources with their jet directed along a random line of sight, just because of geometrical assumptions. We have selected from radio loud quasars good blazar candidates, and we followed up with high energy observations in order to have a confirmation of their orientation and their blazar nature. With this approach, we have compiled and calculated the comoving number densities of accreting black holes with masses larger than 10 to the 9 solar masses in jetted sources. That is the orange line that you see there. And it's compared with the same thing, comoving number density of accreting black holes with masses larger than 10 to the 9 solar masses in all kind of AGN, that is the blue line, okay? And you can see immediately that there is a weird thing. First of all, the jetted sources are not peaking at the same redshift as the overall population, but most of all, the most striking thing is that at very high redshift, not only the fraction of jetted sources appears to be much, much larger than in the local universe, but apparently they are even more numerous than the non-jetted sources. And I know it's quite striking. Probably we have some issues. We are losing some sources because absorption or stuff like that, but you know, it's anyway an impressive and somehow weird conclusion. Here you see all our results in the past. This is updated to a paper that was accepted last week with new blazars observations, and the yellow diamond, it's the highest redshift blazar classified by Silvia Belladita and collaborators that you will hear about in a few talks. So apparently massive, supermassive black holes, the ones that are more extreme, but they are all that we see apparently at very high redshift, seem to prefer forming or at least living in jetted environments, okay, at very, very high redshift. And this is clearly not consistent with the radio loudness fraction that we are observing or other groups are observing. So we probably need to stay away and ignore for a bit the radio loudness to understand and study the jet fraction at very high redshift. And so we decided to go and see if it's a matter of mass. So we decided to select only the most massive sources at such high redshift, regardless of their radio loudness, okay? So we focused on these two guys. These are the only two quasars at redshift larger than 5 that have a mass more than 10 to the 10 solar masses, okay? This guy here is at redshift 5.3 and it's completely radio silenced, meaning that it's covered by the first catalog, first footprint, but it's not detected in radio, so completely radio silent. And the other guy here, 0100, it's a bit farther away, 6.3 redshift, and it's radio quiet, a radio loudness of 0.45. You see that they both have broad emission lines and a typical spectrum of a very high redshift that Roberto showed earlier. In this talk, I will focus on the farther away guy, okay, so 0100, but similar conclusion we obtained also for the other source. If you're interested, you can check the paper or I can show you later on. So both without an indication of a jet presence, so no radio loud at all. Of course, we observed with the VLA, and I wouldn't be here telling this story if it wasn't that we found indication of strong relativistic jets in both of these sources. But this specifically is 0100, and you can see the observations at 5.5 gigahertz and 1.4. And you can see that there is a very strong core emission, very, very bright, very, very powerful, that suggests the presence of a beamed emission and so the presence of a jet in the core. And also, even more strikingly, you see that there is an extended emission that is asymmetric. So we expect it to be a jet that is relativistic in one direction, roughly oriented, not in the plane of the sky at least. So we have an asymmetric structure. The radio powers are striking, and by the analysis of the radio emission, the radio images, and the broadband spectral energy distribution, we could see that the jet power must be in the range of about 10 to the 46 erg per second up to 4 times 10 to the 47 ergs per second, corresponding to two different assumptions on the viewing angle. So it's likely between 16 degrees and 30 degrees from our line of sight, the jet of this source, of this specific source. This is impressive. This guy was very, very radio quiet, okay? So this is something that really surprised us. We were hoping for it, but we were anyway surprised. And of course, we cannot exclude a bit of variability from past observation from here, but you know, passing from completely radio quiet to something that is strongly jetted, strongly beamed with an FR2-like jet is anyway impressive. We also tried to study a bit of the, I won't show you, okay. A bit of the nuclear part, so the mass and the accretion, and we tried to say something, or at least have information on the spin. Here you see the the res frame optical UV spectrum that I showed you before with near-infrared data from WISE. We compared this set of data with different accretion disk models, and we also considered the fact that it can have a spin. So first of all, something that we obtained that with all the models we tried, this is sub-Eddington. This is a sub-Eddington source, and if we consider the effect of the spin, its mass is anyway consistent with the virial mass, so about 10 to the 10 solar masses. It ranges between 4 times 10 to the 9 to 1.7 10 to the 10, and the Eddington ratio correspondingly ranges between 40% to 90% Eddington. Okay. Since we expect that the jet presence is linked to a maximally co-rotating black hole disk system, we expect it to have the largest masses possible and a slightly lower Eddington ratio, but anyway quite fastly creating 40% of Eddington. What does it mean, this? This is another version. Well, first of all, radio loudness at high redshift is not a good tracer of the presence of a jet. So be careful when you calculate the jet fraction from radio loudness fraction, because it can be a problem. Here is the same exercise I showed you before. It's the comoving number densities of accreting black hole, this time with masses larger than 10 to the 10 solar masses. The two set of points are the other guide that I didn't show you, 0306 and 0100, with the different viewing angle assumptions. And these are different curves taken from luminosity function by Shen 2020. And these are the sources that have at least a luminosity consistent with the luminosity of the disks of these two guys. And this is corresponding to 10 to the 10 solar masses black holes accreting at least at 10% of the Eddington luminosity. And you can see that even in the range of 10 to the 10 solar masses, apparently jetted sources are a significant fraction of the overall population of accreting black holes, and this is very striking. It's a strong conclusion, in my opinion, at least. So the problem is, how can jets play a role in building up this kind of sources? Because we already heard that there is a growth problem, okay? This is another version of the evolution of a black hole in the early universe, assuming a standard salpeter timescale for the accretion. We tried to derive the possible seed black holes at redshift 20 that can give origin to 0100, the guy at 10 to the 10 solar mass in redshift 6.3. So this is quite crowded, you know, but you can see that if we assume 40% Eddington ratio that's what we observe for the whole evolution of the black hole, the black hole seeds must be extremely massive, okay? At least 10 to the 7 solar masses. We really need something that is more close to the Eddington limit, and we can reach, let's say, 10 to the 4 or 10 to the 5 solar masses if we assume an Eddington limited accretion. Of course, we need other options, but they always need to include the presence of powerful jets, because they are clearly more numerous than we expected. Of course, we have to consider the direct collapse for a seed black hole that is very massive, but maybe we could assume super Eddington accretion may be linked to the jet presence. I don't know. If you have ideas, I'd be happy to consider them, because we really are puzzled about this. So these are the takeaway messages. So many jets at very high redshift. Very massive sources can host jets, even if they are not radio loud. So check your favorite very massive source at redshift larger than 4 or 5, because they might host a jet. And the radio loudness clearly underestimates the jetted population, and we really need to have a picture that includes strongly the presence of the jet in the early evolution of supermassive black holes. Thank you.
Time for questions. Luca?
Hi, very nice talk. So, would you say that these sources are still radio quiet, according to the conventional definition, right? But since they show a strong jet, as you say, do you think the jet emission may impact on, let's say, the X-ray emission, may contribute it significantly?
Yes. So I'm showing something that is even more crowded than the other picture. Of course, here is the SED broadband emission. We observed the X-ray emission in a very past work of this 0-100, and it clearly traces the corona, even if with a slope that is quite unusual. We assumed that the fact that the lobes are quenched by the CMB radiation, and I think that something about this is in the poster by Luca Ghina, I think, in upstairs. And the fact that there is an enhancement of the X-ray emission, that is the dashed green line here, due to the quenching of the radio emission. And you have something in the X-rays, but it's still anyway very, very faint to be observed. This data of the coronal emission comes from Chandra observation, so it's quite deep. And
but you say coronal, not jet emission.
No, we don't see the jet emission.
Okay. So it's still coronal.
It's still corona because
okay.
with this kind of slope, there is no way that it's a jet, okay? And so we use this as an upper limit to limit the X-ray emission from jets or lobes from the CMB.
Thanks.
Okay.
Any other questions? I definitely have a curiosity because we said when we were... sorry. I'll wait. No, Alessandro.
A very quick question. You said that there are masses of black holes over 10 to the 10 solar masses. And have you considered the fact that when the black hole mass is so large, the accretion disk may be so cold that you don't have enough ionizing photons to create the lines, the emission lines as you observe? Meaning, what if the black hole mass is smaller than 10 to the 10? Maybe
in
10
this
to...
case, you mean? So we have two independent ways of estimating the black hole masses. One that it comes from the literature, from the discovery paper, that is the virial base that you were discussing with Roberto as well. And the other is the this one, that is the fit of the disk. I know it's not as calibrated maybe, but we use different models, and it's anyway consistent with very, very large masses. This kind of approach assumes geometrically thin, optically thick disk that is proportional to the mass. So if we don't, if it were the case that there wasn't enough emission to ionize the Broadline region, we would see, according to the model, the models that are available at least. You see that there is quite a strong contribution in optical UV, not as much as something smaller than this case. So in this case, I wouldn't exclude. In general, probably there is a not very good tracing of the overall population because of this, because maybe we are missing some sources that are not ionized in the Broadline region. But in this case, I would say that they are anyway the most massive we know up to now at this redshift.
Okay, while asking Matilde to come, we had just a curiosity about the size, because you showed the size in arc seconds. What about in kiloparsec?
Sorry?
The size in kiloparsec.
We assumed the extension of 30 kiloparsec in radius for the extended lobe, let's say, and I think it's something of the range, but I will check.
Okay, thanks. Okay, let's thank Tully again. Grazie. So now, Matilde Signorini, University of Florence, Untitled LX-LUV relation, most suitable proxies and causes of the dispersion.
Is the laser...
Sì. Così.
Ecco,
Ti avviso a 3 minuti.
Ok. Sorry. Okay. So, hello everyone, I am Matilde Signorini, and I hope you're not tired of listening about the LX-LUV relation of quasars, because I'm going to talk about it. So, I'm going to discuss some of the most recent results we've been obtaining with this group. And, too sensible, okay. So, the existence of a nonlinear relation between the X-rays and UV luminosity in quasars is an observational result that has been known since decades and which is very interesting for a number of reasons. First of all, the nonlinearity of the relation and its non-variability with the redshift are what allow us to actually use quasars as standard candles, with very intriguing results in terms of cosmology, as also Giada discussed this morning. But more in general, this relation is interesting because it's deeply linked to the quasar physics. It must come from the interaction between the UV-emitting accretion disk and the X-ray corona, but the exact mechanism is still not fully understood. So further investigating it surely can give us insight about how quasars are working. Today I'm going to discuss two issues about this relation, which are the choice of the quantity we use as LUV and the analysis of the dispersion parameter. These are both interesting, both for the cosmological implementation and the physics of the relation itself. A few words on the dispersion already, or other people already mentioned it, but when first discovered, this relation was known to have a very high dispersion of around 0.4 dex, but we know that we can significantly lower it by removing objects that are affected by observational biases. Still, this starting point of 0.24 is still quite high when compared, for example, with supernovae 1A, obviously. So, coming to the choice of the UV luminosity. We have been using as LX and LUV the 2 keV and the 2500 angstrom luminosities, monochromatic luminosities, respectively. But the reason behind these choices are mainly historical. So we can ask if other quantities may work better in terms of obtaining a reduced dispersion of the relation. We should also add that although we do not know the exact physical mechanism, it's clear that the relation will not hold between two single monochromatic luminosities, but will have something to do with the whole quasar emission more in general. So we are simply choosing two proxies, and so we can ask if other proxies can work better. If we now focus on the UV side of the relation, we should also consider that the luminosities we have been using are produced from photometric data up to now, which are it's fine, but at the same time we wanted to see whether deriving luminosities from a spectroscopic analysis would better our results, because obviously for the UV spectrum we expect luminosities derived with spectroscopy to be more accurate, as they can disentangle the true quasar emission from the emission line contributions. So what we did was to do a spectroscopic fit of a sample of 1,800 objects that come from the LUSO 2020 sample and have a counterpart with XMM Newton X-ray observations. We derived the monochromatic luminosities at these 5 different wavelengths, just to check, and of course the properties of the emission lines. So we wanted to test the luminosities relation using these 5 different proxies to compare with them with one another, and also to compare them with the results of photometry. So what did we obtain? The 5 different proxies work more or less the same. We see no significant difference among choosing the 2500 or the 4500 angstrom luminosity. But what we obtain is a slope parameter gamma. No, io continuo a non saper usare sto. Of 0.45, which is significantly lower when compared to the 0.6 that we are used to and that we obtain when we use photometric luminosities. If we look at the dispersion, we see that it's exactly the same. So what we believe that by going with spectroscopy we would obtain a tighter relation turned out not to be true in this sense. But it's also clear that if the true quantity behind this relation was the monochromatic luminosity at one of these given wavelength, we would have get a tighter relation, because there's no doubt that these luminosity measurements are more accurate. As this does not occur, it might be that these two quantities, the photometric and the spectroscopic luminosities, are two proxies, two different proxies of something else, and they work more or less the same. The reasons behind this difference in the slope parameter is something we are still investigating, so suggestions are also welcome. But it surely must have something to do with the fact that in the photometry luminosities, we are also including the contributions from the strong lines and also the iron compounds that can be quite strong for these spectra. So the answer must be somewhere there, and it seems so that this relation actually holds differently in terms of the slope when we are using proxies of different part of the quasar emission. We also tested the relation using the magnesium second luminosity as LUV. We chose this line simply because it's the one which we have for the largest number of objects. And we found a slope which is exactly the same as the one we obtained with photometry, and a significantly lower dispersion of 0.18 dex. Now, we know that the magnesium second line is found at 2,800 angstrom, but its luminosity must depend also on how much magnesium second is there. Therefore, on what is happening on much more, the quasar emission at much more ionizing wavelengths. So maybe the fact that we obtain a tighter relation is suggesting that the physics of the relation might be found at shorter wavelengths, that we are not directly observing, but that we can proxy, for example, with the magnesium line. Now that we have this 0.18 dex of dispersion, we can go and investigate the causes of this dispersion parameter. As I was saying before, we lower it by removing objects that are affected by observational biases, but there are also some factors that contribute to the dispersion which cannot be removed, unfortunately, yet. So we wanted to estimate them in order to estimate the intrinsic dispersion of the relation, which is something important both for the physics behind it and for its cosmological implementation. So the three factors that we investigated are these, and the first one is the X-ray observational issues. I will not go into detail here, but the fact that most of our objects have serendipitous observations in the X-ray comes with a lot of possible problems that we checked by investigating a subsample of objects for which we did a thorough spectroscopic analysis in the X-ray and strong quality check. And we derived that this can contribute to the dispersion with up to 0.09 dex. Then we have the variability of quasars, which of course can contribute to the scatter of the relation. And we tested it by using objects for which we have multiple X-ray observations. And by comparing averaged and single observations, we can estimate it to account to up to 0.08 dex. Finally, the inclination with respect to the line of sight surely contributes something to the dispersion. We cannot test it in the sense that we cannot derive the inclination of our objects with respect to the line of sight, but we try to estimate it with a mock sample of quasars, for which we assumed no intrinsic dispersion and a random inclination in the sky. So for this mock sample of quasar, we obtain, because of the inclination, a dispersion of 0.08. So if you do the quadratic sum of these three numbers, which I did for you, it goes up to 0.15 dex. So of the 0.18 I was showing previously, up to 0.15 can depend on observational issues, so it's not intrinsic to the relation itself. Obviously, there can be dependencies, especially on the redshift, so not for any object the contribute will be the same, but on average we see that the intrinsic dispersion of this relation must be very low, below 0.1 dex for sure. Now, this result is strengthened by another result, which I will only briefly discuss, and you can check Andrea Sacchi's poster for more details. We have a subsample of 30 objects for which we believe that the three factors I discussed previously are the lowest possible. In what sense? For these objects, for most part of them, we have pointed X-ray observations, so the X-ray issues should be the lowest possible. And they are at high redshift, so they have higher average luminosity, which means that the variability and the inclination should be the lowest possible. For these objects, we also performed a spectroscopic analysis both in the X-ray and the UV. And here I show you the stacked spectra. So on the left, you see the X-ray spectrum, and it's perfectly fitted by a power law with a photon index of 1.9, so it's average. And on the right, you see the UV one in black, while in red, you see the Vandenberg spectrum. So this assures us that these objects not only have no visible observational biases in their spectra, but also that these objects are average quasars in both in the X-ray and in the UV. So for this subsample, for which we can say that the observational factors to the dispersion are the lowest possible, if we fit the relation, we obtain this result, which is a dispersion of 0.09. So this, on one hand, assures us, it's relieving in the sense that our estimates are correct, in the sense that for the objects for which we have lower contribution, we actually do observe a lower dispersion. And also, as these three factors must still be contributing something, is telling us that the intrinsic dispersion must be even lower. So this result is significant, well, both for the physics of the relation, because it must be that the physical mechanism is very tight. It's something that is happening in every quasar, also at this high redshift. And in terms of the cosmological implementation of quasars, even if we will not be able to obtain this low dispersion parameter for all the objects in our sample, this is saying us that the intrinsic dispersion is very low, and this gives strength and reliability to also the results we've been discussing this morning about the implementation of quasars as standard candles. So here I leave my conclusions, and I thank you.
Thanks. Time for questions.
Hi, Matilde. Very, very nice work. Did you consider the role of variability in X-ray of some candidates, of which can be the impact of variability of quasars?
It was okay. So for variability, we checked for. What we did was in our sample of quasars, we have some hundred of objects for which we have multiple observations. So what we did was to compare the results of fitting the relation with a single observation and with the average ones. And we lowered the dispersion by 0.08 dex. So in this way, we can estimate that this is the whole contribution. Obviously, at higher redshift, we have lower variabilities, so it will change, but this was the way. We did it for the whole sample because, obviously, we don't have enough statistic to do a proper variability test in small redshift bins, but on average, this should be the contribution.
Thank you very much. I also want to say that this was a really nice talk and really nice work. I like your approach. Very, very detailed, so thank you. And I have a comment, if you can go back to the spectrum, just a very nice fitting you were showing there. And I was just wondering, so do you also use the iron emission, and what templates are you using for the iron contribution?
So we use QuestFit for the fitting of the iron template, and it accounts for a sum of different templates. I don't even, I cannot tell the details, but it's a quite simple fitting because we had to do it for this number of objects. So obviously, I did not do one by one. It was a routine fitting.
So it was done automatically for all this?
Yes, like we did some tests and set the priors, but then it was done routinely. And so we had not tested the iron compounds in the sense of using them as a UV proxy for the relation, because obviously being different templates with different relative weights, it's not so easy to understand what is happening there. But we took them into account in the global fit. That's okay.
Thank you very much. Very nice plot.
Thank you.
Any other questions for Matilde? Just a curiosity, what about the time scale for the variability, to account for the variability? Do you have any rough idea how many observations you need in order to check it better, like the spanning, for example, between the observations?
I have no clear answer, also because as the observations are all serendipitous, we had no...
also for the golden sample?
No, but for that we have one observation in the one pointed observation in the X-ray. So if we were granted more, maybe we could check for this. But for the other objects for which we have serendipitous one, we had no say in telling the times. So we have very different time scales. So we just average for all of them, but we're not able to test if averaging the one for which the time lag is bigger gives better results, because we have no enough statistic for that yet, hopefully.
Thanks. Let's thank Matilde again.
Thank you.
Now is Luca Zappacosta. Hyperion, year 1, an X-ray preview of Titan quasars at the reionization epoch.
Hi, everybody. Hello. Huh? So I'm going to present Hyperion, which is a program based on a multi-year heritage program, XMM Newton, focused on the characterization of high redshift quasar, redshift larger than 6, at the epoch of reionization. Hyperion is a large collaboration of 40 scientists, many of them are here, in 20 different institutes. Basically, so far, more than 200 quasars have been discovered at redshift larger than 6, and you can see in this plot I can do it. You can see in this plot their distribution in bolometric luminosities and supermassive black hole mass, and you can see here that these objects emit as a high fraction of the Eddington luminosities, with lambda Eddington larger than 0.2, and they have masses very large, exceeding 10 to the 8 solar masses, which are comparable with masses measured in the local universe. And the importance of these sources, I can do it, lies on the fact that they must have grown very fast, less than 1 giga a year. And assuming an exponential continuous accretion at the Eddington rate, you can see that they must have grown with an initial seed mass of 10 to the 4th. But you can relax the assumption of continuous accretion, so the duty cycle of Eddington accreting, and if you just decrease by a factor of 2, you need 10 to the 6 seed black holes. And other mechanisms have been devised to understand their formation, like supercritical accretion of black hole coalescence. So the fundamental challenges posed by their existence spurred extensive multi-wavelength campaigns with the flagship observatories, but these sources are faint. They require time-consuming observations. You can see here in this plot the progress of the discovery of these sources as a function of year, and their characterization as a function of the bands, so submillimeter, near infrared, X-ray. As you can see here, the X-ray is less efficient and less sensitive band. For all these reasons, the characterization of the sources may suffer from observational bias, since these sources, the characterization of the sources, often done for the brightest sources or the farthest one or the most peculiar one. And basically, we may have a biased view of these sources with a heterogeneous QSO sample and a poor X-ray characterization. But the X-ray is very important because they provide information on the innermost accreting regions of these quasars. And typically, the X-ray spectrum of the sources take the form of a power law photon index with a canonical gamma a slope of 1.82, which falls off exponentially at higher energies above 100 keV. And there are also other modifications of the spectrum, like the addition of a Compton reflection amp 20-30 kV. So far, the characterization of these sources have shown that there is almost no difference, except with a few mostly contrasting marginal indications, like the steepening of gamma. Marginal evidence have been obtained by Fabio, and presence of faster or more prominent nuclear winds or overgrown black holes compared to their host mass. But to understand if these differences, are significant and not biased by the selection of these sources, we need homogeneous and high-quality investigation for these sources. So we decided that it was about time to start this investigation, starting from the X-rays, because it's, as I showed you, is the band where the characterization is less secure. And furthermore, there is a 30-year gap between the current flagship X-ray observatories and the currently still planned Athena X-ray Observatory. While in the middle, plenty of facilities at other wavelengths have been built and used to characterize these sources. And furthermore, having good X-ray data, it will be helpful for current and future characterizations starting from data from other wavelengths. And we wanted to obtain a more reliable characterization of the X-ray population of quasar at redshift larger than 6. So we decided, given the peculiarity of the sources, to start the characterization, their selection with their extreme supermassive black holes. So we selected only sources in our sample which required a seed black hole mass larger than 1,000 solar masses. So these are the titans among redshift larger than 6 quasar, those that accreted the most mass at their epoch. The sample consists of 17 quasars, a redshift between 6 and 7.5. These are hyperluminous sources with volumetric luminosity exceeding 10 to the 47. They have masses between 10 to the 9 and 10 to the 10. In December 2020, we got approved a multi-year heritage XMM program, which consists of 2.4 megaseconds observation on the Hyperion targets to be observed in a 3-year time span. This is the 4th largest XMM Newton program ever approved. And this program will provide unprecedented quality spectra for such a large sample of high redshift sources by giving an increase, a factor of 7 on the spectral quality of archived sources, and at the end by increasing the number of sources with such quality spectra by a factor of 5. And Hyperion will provide unprecedented constraint on nuclear properties, accretion, ejection, and this corona complex. So, okay. Now I'm going to show you a little preview of the first year of observation. There is also, so far we have observed 10 QSO, partially observed, plus 2 archived quasar which were had in the archive already good quality data. We collected basically almost 1,000 counts with a total of 938 kilosecond observations. And I'm going to show you the spectrum of the redshift larger than 7 quasar observed so far. Basically, the two sources have gamma very steep, 2.6, which is very steep compared to the canonical 1.8 to gamma observed at lower redshift. So we decided to do a joint fit of all the data sets. For 12 QSO, these are 36 data sets with a simple power law model. And we got gamma 2.35, which rule out a canonical gamma at 3 sigma level. We can put our data here in this plot to see if these marginal indications are confirmed. Well, you know. This is all the sources with large error bar, but our plot or our joint fit, it's very significant. Now we have to decide if this is a genuine redshift evolution, or this is due to the fact that these are hyperluminous sources or are Eddington accreting sources. We compare them with lower redshift analogs, the Wish quasars, which are analogs for the bolometric luminosities, which is similar to the one of the Hyperion sources, and they have a gamma canonical. We compared also with the high Eddington sources from the Laurenti 2021 work, and they still have canonical gamma, average, of course. So it seems that this is a genuine redshift evolution. But of course, a steep gamma can be mimicked if the power law is modified by a cutoff at lower energy. So we repeated the joint fit, this time with a power law plus a cutoff. And this is the 1 sigma 90%, 99% confident contours for the photon index and cutoff energy. And basically, a best fit return 2.2 gamma with a 50 keV cutoff. If we fix gamma to 1.9 canonical, we get a cutoff of 20 keV, which is very low. If it is true, if there is indeed a cutoff at the energies probed by our observation, this would be the first measurement at the epoch ionization for hyperluminous quasars. So basically, these are my conclusions. So we proved with our sample that these quasars are intrinsically different, at least according to their accretion properties. And the future is bright because we have 2 more years of data which are awaiting us. And we have embarked on an aggressive proposal campaign in the near infrared, the submillimeter band, in order to characterize other properties on the bright line region and also on the host galaxy properties of these quasars at the epoch ionization. And I'm happy to answer to your question and leave you with a short story.
Thanks, Luca. So, questions?
It's just a clarification because I think I missed it. But how is the Hyperion sample selected? So what are the properties? You said that this is an homogeneous sample of quasars. In which properties this sample is homogeneous?
It's not homogeneous. It's a physically selected sample. Not
a physically selected?
Yes, because they are selected according to their mass growth, extreme mass growth. These are the sources which accreted mass the most to get their billion solar masses. So the sources which needed more than 1,000 solar masses black hole seed, those ones. Those that you can have more difficulty in explaining with your favored theoretical model, okay?
Any other questions for Luca?
I guess that, the quality of the X-ray data was not able to eventually probe also the presence of a soft excess, or instead it was ruled out?
Because the redshift shifts the soft excess band out of the
sorry.
band. Yeah.
Time for last quick question. Oh, Luca, just a curiosity. The upcoming observations will be follow-up of this because you already got 10 out of 15?
Part will be follow-up of this, and part will be new sources.
New sources, okay.
5 other sources, yeah.
Okay, let's thank Luca again and Alessandro. Okay, so Alessandro Trinca, the low end of black hole mass function and cosmic dawn.
Thank you. Hi everyone, I'm Alessandro Trinca. I'm a PhD student at La Sapienza University, and today I'd like to present you this recent work that we published in collaboration with the people listed here, which has been focused on the mass distribution of black holes at the cosmic dawn, and with a particular focus on the low end of the mass function. Now, as Luca, just showed us, okay. Many quasars observed at redshift higher than 6, and many of them are extremely bright sources, suggesting that they're powered by billion solar masses black holes already in place where the universe was less than 1 gigayears old. So one of the long-standing questions for theoretical models is how do they grow so massive in such a short time scale? But we also know that these objects are actually just the tip of the iceberg because we're starting to observe a much wider population of low luminosity AGNs powered by less massive black holes thanks to many facilities like the Shell-Q survey, which explored the AGN luminosity function down to very faint magnitudes around redshift 6. And these objects actually are the most promising candidates to explore the mechanisms of early black hole formation and growth. In fact, we can have different mechanisms for the formation of the progenitors of these massive objects that we call seeds. We have the most common scenario, the formation of a light seed as a remnant of the third generation of stars, and this can occur at very high redshift, leading to the formation of black holes up to a few hundred solar masses. On the other side, you can have very heavy seeds formed through the so-called direct collapse scenario under some particular conditions for the host galaxy, up to 10 to the 5 solar masses. And in between, we can also have medium-weight seeds through runaway mergers inside dense nuclear star clusters. But that is just for what concerns the formation of the seed. Then you have to grow. It has to grow through cosmic time to reach the observed mass luminosities. Usually, a standard Bondi accretion is assumed, where the accretion rate depends only on the gas density around the black hole and the black hole mass. And this is assumed to be a relatively efficient accretion, so it's usually kept at the Eddington limit. But several models show that under higher accretion rate and inflow of gas, we can have the formation of a slim disk, which is optically thick, so we can actually have photon trapping, the relative efficiency drops, and we end up with accretion rates much higher than the Eddington 1. So the main focus of our work has been to investigate this poorly explored population of low luminosity AGNs at high redshift and try to constrain from their mass and luminosity distribution the underlying accretion model. And to do so, we developed this new cosmic archaeology tool, CAT if you want, which is a fast semi-analytic model that enables us to have a large statistical sample of the galaxy population, a redshift higher than 4, in order to explore the early coevolution between nuclear black holes and host galaxies. And this has been built upon the well-tested Gamete quasar dust model originally developed by Rosa Valiante that has been used extensively and successfully to explore the formation and evolution of the brightest AGN at high redshift for what concerns both the different seeding mechanisms and the relative observational signatures, like in these two recent works. But the strength of this new model is that now we are able to expand this analysis to a much wider range of masses and diverse environments, because we reconstruct actually more than 100 major trees starting from redshift 4, and now we are able to follow the baryonic component inside dark matter halos from the 10 to the 6 mini halos, a very high redshift, where we form the first POP3 stars, up to the 10 to the 14 solar masses halo, where we host actually bright quasars. And this enables us on small scales to follow the formation of both POP3 remnants and direct collapse black holes, and accordingly to the environmental condition, of the host halo and follow then their accretion and mergers through cosmic times. But at the same time, on a larger scale, we can follow the entire high mass and low mass end of the black hole population. So we calibrated the model for these reasons to reconstruct both some observational properties of the brightest object around redshift 6, but also some global constraints for the galaxy population. And as an example here, I showed you the star formation, our prediction in red for the star formation rate density, and also for the bolometric luminosity versus black hole mass relation, compared to several observational results. Once the model has been calibrated, we assumed standard Bondi accretion, Eddington limited, and we have been able to reconstruct the black hole mass function at different redshift. Here we have the number density of objects as a function of their mass from redshift 18 down to redshift 4. And what we see is that black hole descending only from light seeds, so POP3 remnants in magenta, and black holes descending from at least one heavy seed in red are clearly detached on the mass distribution. And that reflects the stunted growth of light seeds that are not able to accrete efficiently through cosmic times. And of course, we compared, despite they are formed, of course, at very high redshift. And we compared our results for the high end of the mass function with several models, both from hydrodynamical simulations, semi-analytical models, and with some empirical relation, finding a pretty good agreement with them. But still now, this clear gap that we see below around 10 to the 5 solar masses is reflected on the AGN luminosity function at high redshift. Here you see our predictions for the X-ray luminosity function in the central panel and the UV luminosity function in the right panels from redshift 4 to redshift 6. And our results are the black dots compared with several observational points. And what we can clearly see, mostly in the X-rays, because for the UV, this gap lays at very faint magnitude, is that we have a very sharp drop of the luminosity function below a certain luminosity. So we ask ourselves, but what if we actually change the accretion mechanism? So at first, we just removed the Eddington cap for the accretion rate. And what we found is that this is not the reason why the light seeds are not accreting, because we still find this gap, but we also failed actually reproducing the high masses observed at redshift 6, since the black hole feedback is too strong at early times. So we decided to completely change the accretion paradigm, assuming a simplified scenario where we have that the black hole growth is mainly driven by very brief periods of enhanced accretion triggered by major galaxy mergers. When we assume strong inflows of gas toward the central region of the galaxy with the formation of a slim disk around the black hole and an accretion rate which is proportional to the gas mass inside the galaxy. And what we found is that with just this simplified model, we are able to pretty match the distribution of the high mass end below redshift 6 with respect to the reference model, which is the one in dashed lines. But more than that, we now fill this gap because light seeds are able to accrete efficiently. And this is telling us that it's not the environment that is mainly limiting the growth of light seeds, but mostly the way the gas is funneled in the central regions. But of course, this again reflects in the luminosity function of AGNs. Here we see the difference for the reference model and the merger-driven one. And apart from a different normalization in the bright end, which is due to an intrinsic difficulty in modeling the luminosity function for these briefly accreting black holes, we found actually that the main difference lays at faint luminosity, where we do not have now this very sharp drop in the luminosity functions. But of course, this main difference lies at very faint magnitude. Just as a reference here, this gray vertical dot line represents the predicted sensitivity limit for links. So it will be very difficult to test observationally. And, And of course, this different accretion mechanism reflects also in the black hole galaxy coevolution, since we can observe in the left panels that in the case of the simple Eddington limited Bondi accretion, we find quite a symbiotic evolution between nuclear black holes and galaxies with respect to the local scaling relations, while for a merger-driven scenario, we expect something like more a black hole dominance, and then the local relation is retrieved at later times. So to conclude, it seems to us that the key element affecting the efficiency of light black hole seeds is mostly the way the gas reaches the central region, so the physical mechanism that is driving the black hole growth. Since if we assume this merger-driven scenario, they are able to contribute substantially to the building up of the high mass end of the distribution. But the main difference resides in the faint end of the luminosity function, so it will be very challenging to probe observationally, even with the next generation of surveys. Still, CAT might be a very powerful tool also to make prediction for the merger rates of gravitational waves that should be observable with future interferometers, and this will help massively to discern between different accretion and seeding scenarios. So, thank you for your attention, and I'm taking questions.
Thanks, Alessandro. Questions?
Thank you, Rotto. Can you go back to the luminosity function? Next slide, I guess.
The comparison or the
comparison?
Okay.
I think this one, yes. Can you comment again on discrepancy at the bright end about your expectation and the observations?
Sure. Okay, in the reference model, in the reference model, we're actually able to quite match many observational results, in particular the one that are, let's say, we match it, assuming also as an obscuration, a simple model for obscuration that is this shaded region. While for the merger-driven model, here we have an intrinsic difficulty because actually we are limited because we don't know which is the time scale of these very brief periods of accretion. So we are limited by the time resolution of our model, so we probably are systematically underestimating a little bit the luminosity. And more than that, actually, in the bright end, the contribution of merging system more than quiescent one is large. And so we do not account at all for small-scale obscuration. So I expect that actually this will impact a lot on the bright end because actually this bump of system in the bright end that you see here with respect to the best fit model, let's say, that is the dashed black line, is represented by this merging system that should be heavily obscured with respect to the quiescent ones.
So, put in another way, if the merger-driven model is correct, we should expect a lot of very obscured sources at our redshift.
Actually, the system accreting in this brief period of enhancement should be heavily obscured to match the obscuration.
Thank you.
Thanks. Any other questions? Just a technical curiosity, I lost, I think it was slide number 7 for the calibration. You calibrate on the high energy tail in the redshift distribution in mass?
We actually, it's just an example, we actually calibrate both on the properties of high redshift quasars such as black hole mass, but also stellar mass, dust mass, and so on. But at the same time, we also want to reconstruct the star formation history of the global population of galaxies. So here we see the comparison for the star formation rate density. In red, we have the global population, but we have to correct for the let's say the galaxies that are actually observed by surveys. So we have this dashed line that fits quite well the results. And we do the same for the stellar mass density as an example.
Thanks. Let's thank Alessandro again. Thank you. Thank you. Now, Fabio Di Mascia, AGN imprints on the infrared emission of galaxies at the epoch of ionization again, and AGN imprints.
Okay. Hi, everybody. Good morning. I'm Fabio Di Mascia, and during this talk, I will show you my results regarding AGN imprints on the infrared emission of galaxies during the epoch of ionization. So I think you already heard many times this morning that we know so far more than almost 300 of quasars at redshift around 6, thanks to several sky surveys in the last 2 decades. These sky surveys were able to probe the optical near-infrared emission of these galaxies, which means that they probed the rest-frame UV emission at this high redshift. And here you can see the UV luminosity function at redshift 6, estimated by recent work by Arikane and Matsuoka. However, if we consider if we try to extrapolate the X-ray luminosity function of AGN from redshift 3 to 4 up to redshift 6, we see that there is a huge gap. There is a huge gap between the two, which means that maybe, is this suggesting that maybe we are missing the bulk of AGN population at this very high redshift? And if so, this means that this AGN will be obscured, likely, in the UV. So it is possible maybe to find them from the infrared. And this is the first point that I will talk about during this talk, if there are infrared signatures of high redshift AGN. And the second point that is strictly connected to the first is what is the impact of AGN on their host galaxy properties. And I will mainly talk about the dust temperature. So in order to address these questions, we started from cosmological zoom-in simulations, adopting the suite by Bahrain collaborators 2018, in which a 10^12 solar mass halo is followed from redshift 100 down to redshift 6. Here I'm showing you an example of the gas density distribution for one of the runs performed at different snapshots. These simulations are carried with the Gadget 3 code, with the standard prescription for stellar physics, and an additional prescription for black hole seeding and growth that allow for the formation of 10⁹ solar mass black hole at redshift 6. I will focus in particular on 2 runs in these simulations that differ for the way in which the feedback from black holes is implemented. In one case, energy is injected onto the surrounding gas with a spherical symmetry. I will refer to these simulations as AGN sphere. And in the other case, which is AGN cone, feedback is distributed in a bicone. And the different feedback has an effect on the evolution of the black holes in these 2 simulations. Here I'm showing you the evolution of the accretion rate as a function of redshift for the most accreting black hole, for the most massive black holes in the 2 simulations. In red, you see the AGN cone case, and in green, the AGN sphere case. We see that on average, throughout the history of these halo black holes tend to accrete much faster in the case in which conical feedback is implemented. And as a consequence, the black hole mass that these black holes reach in the AGN cone case are higher by almost by an order of magnitude between the 2. So given that these black holes in the AGN cone accrete faster, this also means that they are likely intrinsically brighter. So I will also refer to the AGN cone case as the case with bright AGN and to sphere as faint AGN. So here is an example at a snapshot on which we focused our analysis. I'm showing you here in the middle panel AGN sphere and on the right panel AGN cone, and comparing here the gas distribution of the most massive halo with the control run in which black holes are not implemented. I don't know if you can appreciate from the colors, but when feedback is implemented, the gas density tends to decrease because gas is pushed away from the black holes. And given that the star formation rate that I'm showing you here is implemented with a density-based criterion, also the star formation rate is suppressed. And for this particular snapshot, it is suppressed by a factor of 2. When spherical feedback is implemented, by a factor of 3 when conical feedback is implemented. So, but the point is, how will these galaxies will look like to actual observations? In order to do so, we perform the radiative transfer calculation by employing the code SCIRT, which solved the radiative transfer problem in a Monte Carlo fashion and through dust. And we are able to simulate the UV to infrared emission of these galaxies. Here I'm focusing on the AGN-Con case. Here I'm showing you again the gas density distribution. Given that we do not follow explicitly dust in these simulations, in the post-process analysis we have to assume a dust component that I'm showing you here, the dust distribution, by adopting a uniform dust-to-matter ratio and dust properties that reproduce the SMC extinction curve. We of course included stellar radiation, and we also added an AGN component, which is modeled with a composite power law emission, and setting the bolometric luminosity proportional to the accretion rate of the black holes, in order to be consistent with aerodynamical simulations. So here is an example of the snapshot that I'm showing you before on how will we see these galaxies. On the left I'm showing you the UV emission, and on the right the infrared emission. And the first thing that you might notice is that we see four bright sources in the infrared that I'm labeling here with letters from A to D. 3 of these sources, A, B, and C, are actually galaxies that host an AGN. And you see that only one of them is visible in the UV, which is source A. This source is the UV brightest, but the black hole that is powering this AGN is not the most accreting black hole, which is instead the one in source C, which is the far infrared brightest source. So this system is essentially, to an observation, will look like the quasar galaxy, plus another companion galaxies that will shine in the infrared, and then it will look like a sub-millimeter galaxy companion. And this is something that recently we are finding also in observations. And the first one to find something like this was Roberto De Carli and collaborators in 2017, in which they find 4 companion galaxies in the sub-millimeter galaxies in the field of 25, if I'm correct, quasar galaxies. We also directly compare with, the data by De Carli and collaborators. I'm showing you here the spectral energy distribution for the 4 sources. I'm keeping the same color legend. So in the infrared, we should look like at a green curve that represents the infrared bright source. And we see that it's consistent with the results by De Carli. But this source will be missed by HST. This source will actually be missed by HST, being faintest at the deepest HST observation that we currently have. And JWST will probably help us in finding these obscure sources, for example. And I will follow up more on this. How will, given that this source is actually a dust-obscured AGN, how can we detect this in other ways? We look at a spectral energy distribution of at the same snapshot again for the AGN-Con case, so the bright AGN, the faint AGN case, and compare with the control run. And we consider the infrared and mid-infrared flux for this 3 run. We notice that the ratio far infrared to mid-infrared for the no AGN case is of the order of 100 and 1000, depending on the wavelength where you compute it. Whereas if we consider a faint AGN, this ratio drops to 10. And for a bright AGN, the mid-infrared flux is almost comparable to the far infrared flux. So as a consequence, we find that the AGN radiation boosts the mid-infrared flux in the host galaxy. And this implies that if we employ a synergy between infrared facilities like ALMA and JWST, or possible mid-infrared facilities in the future, like the proposed Origin mission, we might be able to unveil faint or dust-obscured AGN. Finally, why do we see this mid-infrared excess? And the reason is related with the dust temperature in the host galaxies of this AGN. If we consider, on the left I'm showing you again the spectral energy distribution, and on the right I'm showing you the PDF of the dust temperature, in which the blue histograms show the mass-weighted distribution, so probing the bulk of the dust component, whereas the red, the luminosity weighted, therefore probing the brightest region. We see that the dust component is relatively cold, between 30 and 60 Kelvin, in these galaxies where AGN are not included. However, when we include AGN radiation, we find that a component, a warm component with temperature higher than 100 Kelvin, and which shines a bit more in the mid-infrared, therefore shifting the SED peak towards shorter wavelength. And this component is even more prominent when the AGN is bright, at the point that, constituting only 0.1% of the total dust mass, it provides almost 50% of the infrared flux. So we find that at the end, the AGN can effectively hit the dust in the Ross galaxy. So now I will briefly summarize what we did. We performed radiative transfer calculation of Redshift 6 quasar-Ross galaxies. We find in these simulations a merging system that is consistent with ALMA and HST observation of quasar plus sub-millimeter galaxy companions. And we find that in these galaxies, a warm dust component with temperature higher than 100 Kelvin that is mainly radiated by the AGN coexists with a diffuse component that is mainly radiated by stars. And this component boosts the mid-infrared flux. Therefore, it suggests the possibility to unveil faint and/or dust-obscured AGN via the mid-infrared to far-infrared flux ratio. And thank you for your attention. I'll be happy to take your questions.
Thanks.
Very nice presentation. I had a couple of questions. One is what happens to the dust torus? Because I'm surprised that you should see it appearing irrespective of the obscuration. And the second, in terms of the dust temperature, you say that it can rise up to hundreds of K. So we don't see this in any of the Redshift 6 quasar studies so far. But I guess we don't see it once we consider on the entire galaxy. We don't have the special information that yet on the temperature. I was wondering if you can tell something about where this temperature should be, this high temperature component should be. Is it for most of the ISM or only the very center? Thanks.
Yeah, those are two very, very important questions. So. First of all, I should mention that in these simulations, we, in the post-process analysis, we use a simplified model and we did not include the dusty torus. So these have essentially two effects. The first one is that we have less obscuration of the UV, and so there is a higher UV flux that can hit the dust from the AGN. But at the same point, we do not have the mid-infrared contribution of the dusty torus to the SED. And this will be very difficult to do an estimate of how this it will impact the SED. Regarding the second point, this is a very important point. Given that we post-process the simulations, we have access to the spatial distribution of the dust temperature. And therefore, instead, when we perform an observation, we only look at the SED and then we perform the SED fitting and we derive one parameter to represent the full dust temperature distribution. So from the resolution that we have in our simulations, we find that this warm dust component is localized around in the closest regions of the ISM to the central galaxies, so on scales of hundreds of parsec at least. So in the very central region, essentially.
Any other questions for Fabio? Okay, so let's thank our speaker again. Thanks. Grazie, Fabio. So it's now time for... Okay, here he is. Here she is. Silvia Belladito, the PSO J0309 plus 27, the first blazer in the reionization era. Thanks.
Okay. Hello, everybody. As already Roberto and Tulia said this morning, make me a little bit anxious now about this presentation. I will talk about PSO J0309+27 that I will call PSO for entire talk for simplicity. That is the first blazar discovered at Russia above 6 at the end of the reionization era. As already said, in these days, blazars are radial IDGN with the relativistic jet pointing toward the Earth. We usually define a blazar to have a viewing angle less than 1/gamma, where gamma is the bulk Lorentz factor of the jet. And so thanks to this peculiar orientation, blazars are very bright, visible up to high redshift, but more important, they have a statistical relevance, because for each observed blazar at a given redshift, we know there must be hundreds of radial outsources with the jet pointing elsewhere with the same characteristics. And so blazars, Okay, so blazars allow us to make a complete census free from orientation bias of the total radial IDGN populations at a given redshift, and so their supermassive black holes. We usually said find one to count 100 to better emphasize every single blazar discovery. And make a complete census of high redshift radial IDGN is very important to understand the role of relativistic jets in supermassive black hole growth. Before PSO discovery, the most distant blazar was at redshift 5.37, and it was discovered in 2004, so very long time ago. And only few blazars were discovered at redshift above 5, 3 of these in 2019. And that's why we decided to search for blazars in the next spin of redshift, trying to break the barrier of redshift 6. And so by cross-matching the MVSS radio catalog with the Pan-STAR optical catalog and the WISE middle infrared catalog, and by using the dropout technique, that is the common technique used to select high redshift AGN candidates, we select a little sample of candidates. One of these was an already discovered radial IDGN at redshift 5.8 that allow us to say that our selection method was valid. And among the other observed candidates with a spectroscopic follow-up, we discover our PSO that turned out to be a radial IDGN at redshift 6.1. And you can see here the discovery spectrum taken with mods at LBT with the Lyman alpha line. Here in the table there are some photometric characteristics of the source. And as you can see, the flux in the radio band is very high, making PSO the radio brightest object at redshift above 6 ever discovered. 3 were the characteristics that allow us to say that PSO is not a common radial IDGN but a blazar. First, the flat radio spectrum. We measure a flat spectral index between the two radio detection available at the time of the discovery, the TGSS at 150 megahertz and the MVSS at 1 gigahertz. Second, the very high value of radio loudness, larger than 2000, that suggests that the radio emission coming from the jet is dominating over the optical emission coming from the disk. As you can see from the plot, the radio loudness of PSO is the highest ever measured at redshift above 5.5 today. And the last but not the least, the very high, the very intense X-ray emission, as you can see from the set of the source, that is stronger with respect to the emission expected from an X-ray corona of a radio quiet AGN with the same optical luminosity of PSO. And moreover, the X-ray emission is flat. The photon index is typical of blazar. And so we classify PSO as a blazar, the one and only at redshift above 6. And so we decided to carry out different follow-ups in different bands because this source is unique, and so we want to understand better its properties. And first, I show you the central engine of PSO, what's the black hole its host. Thanks to a spectroscopic follow-up with the LBT telescope, we detect the C4 broad emission line, from which we calculated the black hole mass with the virial single epoch method. And by using this equation found in the literature, we measure a mass of 1 billion solar masses. That is a monster black hole. We had a redshift above 6. The universe was less than 1 billion of years. And so, as already said in this day, it's challenging and it's very difficult to explain such a large masses in their high redshift universe. What we did in this sense was to take simple analytical black hole growth models and trying to reproduce the mass of the seed of PSO. As you can see, the models have different parameters, and we made some assumptions based on what we found also in the literature. For example, for the efficiency of the accretion process, we use both 0.1 and 0.3 that are typically not spinning black hole and rotating black hole. We used the observed value of the Eddington ratio, 0.4, and the value equal to 1, the maximum value allowed in a Eddington limited accretion scenario. We suppose the black hole to be active for all the time of the growth, and we set the start of the growth at redshift 30, where the first galaxy and star are thought to be formed. These are the black hole growth curves that we obtain with the error bands, and the horizontal bands represent the mass of the black hole seeds predicted from the models. What we found, thanks to the image, is that an efficiency of 0.3 is not realistic because it requires very massive black hole seed not predicted from the models, and it's not realistic even if PSO is a jetted black hole and is a jetted AGN, and usually jetted AGN are associated to a highly spinning black hole, highly rotating black hole. We know that the situation of black hole growth is complicated. We have to take into consideration a lot of things. Some possible solutions already decided in these days are invoke super Eddington accretion episode that boost the growth, or for radial out sources, we can take into consideration a solution, for example, explained by Ghisellini and collaborator in 2015, that say that not all the gravitational energy of the infalling matter is converted into radiation, but only a part, so it's involved in accretion process, but only a part of it. Another part of the infalling energy, it's the energy of the falling matter, is converted into magnetic energy that is a necessary ingredient of the jet launching. And so the total efficiency of a radial out AGN could be 0.3 or 0.4, but only a part of it, it's the one involved in the accretion process. For radial out AGN, we also have to take into consideration the role of the environment, because radial out AGN are usually found to live in the most dense environment at any redshift, environment full of star-forming galaxies, Lyman-Bray galaxy, Lyman alpha emitters. That simulation said that the continuity interaction between these galaxies and a central AGN could trigger the radio jet activity, spin up the central black hole, and so in some way affect the black hole growth. That's why we decided to study the environment of PSO by searching for Lyman-Bray galaxies in this field. And I'll show you here a preliminary part of this project. We select by following the same selection method used for the successful project on J1030, that is a radio quiet AGN at redshift 6.3, on which Marco, after me, will give us a lot of results about this quasar. We select a sample of LBG candidates in the field of PSO that you see in the image, on which we required a spectroscopic follow-up. And we know that based on the result of J1030, that the confirmation of a few of these LBGs will allow us to detect the overdensity around PSO. And if this will be true, this is the first overdensity around the radial out quasars at a ratio above 6. So stay tuned for some results in this case. Before concluding, I just want to show you the radio properties of the source, the radio jet of PSO, because I think it's very amazing. At the moment, we have different radio images of the source on arc-second resolution above and sub-arc-second resolution. The images that we obtain with a follow-up with the VLBA telescope that we published in a paper led by Cristiana Spingola. All these images show that the source has an extension in the northeast direction, both on kiloparsec scale, the images above, and parsec scale, our VLBA image. So the extension of this source, the jet, is in the same direction at all scales. No sign of counterjet, suggesting that the source is seen under a small viewing angle. And now, for better tracing the jet seen in the TGSS image at 150 megahertz, we obtain a low-far follow-up. And I'll show you here a preliminary results on this project. This is the red contours are the low-far image at 150 megahertz that we have. As you can see, the source is clearly detected, it is marginally resolved, the extension is real also on this scale, very far away from the black hole on 100 of kiloparsec scale, but this extension seems to be in another direction, not in the northeast direction, but in the east direction. So for some reason, the jet very far away from the black hole changes direction, and we are working on this data. Cristiana is working on this data also for understanding this reason. If you want to know something about the X-ray properties of the source that are also interesting too, you can read the paper by Alberto Moretti on the rapid X-ray variability of the source, or you can talk with Alberto today, and see Luca Higuina's poster of the detection of the X-ray jet also with Chandra. And so for concluding, we discovered PSO, the one and only blazar redshift above 6, and how many PSO we can discover in the next year thanks to the new generation of surveys. And the answer is a lot. We have, and we will have, a new generation of surveys both in the radio band or in the optical infrared band, in this case from ground-based telescope and space telescope, that will be deeper with respect to the surveys available at the moment, like the MVSS in the radio or the pan-stars in the optical. So the combination of these surveys will allow us to select more and more blazars at the highest redshift. For example, the combination between LSST and DIMU will allow us to select 100 of blazars at redshift above 4 and tens of blazars in the rear ionization epoch. And so we will be able to select larger and statistically complete sample of blazars, doing statistical study on the blazar population, on the radio loud DGM population. And so we have only, at the moment, wait for these surveys to select and have a larger sample and not only one object. And so thank you so much.
Thank you very much, Silvia. Time for questions. Just one question about VLASS, because I thought for the initial selection I would start with VLASS other than MVSS.
Yes, but the VLSS data are not, the VLS surveys is not complete at all at this day.
The Epoch 2.2 is almost covering...
But not at the time of the discovery
when you did
selection of this source. And so we select from the MVSS and when we search for the detection in the VLASS.
By the way, I can tell you that for LOFAR there is a paper by Mooney that actually left astronomy now, but it shows a lot of extended emission in blazars with the LOFAR data, 150 megahertz.
Okay, so thank you for the paper.
Okay.
Very nice talk, Silvia. I was wondering what do you think is the bottleneck in the discovery of this very high redshift blazar? The fact that we don't have significant coverage in the radio, or the fact that where we have the radio doing all the selection of the counterparts and so on is excruciating?
I think that now our problem in this type of selection is the lack of optical surveys that cover a large fraction of the sky but are deeper with respect to the pan-star that has a magnitude limit similar to that on the of the SDSS, so 22, 22.5. We need LSST in this case because we have to go deeper with the optical counterpart. Radio surveys like the last I cited, the RAX survey, are deeper with respect to the MVSS just now at the moment, but we lack the optical counterpart.
Any other questions for Silvia? So let's thank our speaker again. Okay, now is Marco Vignoli for J30, no? Web of the Giant, a large-scale structure around Z6.31, quasar SDSS J30 plus 0524. Mi chiama lui, vero? No? Ha detto. Ok.
Good morning. My name is Marco Mignoli, and probably you already know that I'm one of the few survived to all the AGN Italian meeting. And probably the secret is that at a certain age I give up to play football in the match during the AGN meeting. Okay. Someone don't understand this advice. And okay. I'm here to present you the Web of Giants, the first large-scale structure discovered around a supermassive black hole at the high redshift greater than 6. It has been a very long work. It lasted 10 years almost, and a lot of collaborators work on this project. And among them, Roberto is by sure the J1030 soul, the boss. So we start at Gen 10 and we finished at the Gen 14. No, we finished at the COVID time, and we published the paper in the summer 2020. And we also got an ESO press release about the result. As you can see, the Web of Giants is the fact that we spectroscopically confirm the presence of 6 galaxies around the bright quasar Gen J1030 that hosts a supermassive black hole, the Giant, that has a mass of more than 1 billion solar masses. And you already heard a lot of time the very challenge of the AGN astrophysics at high redshift is how to understand how this supermassive black hole grow in so fast, in less than 1 gigayear, and what is the origin. And also, my point of view that I'm mainly a spectroscopic observer, why they are so indistinguishable also in the spectra, ultraviolet and optical spectra from the quasar today. And the fundamental question, when, where, and how they form and grow. And our group concentrates on the second part of the question. So this is a long project. Some of you already heard this, all the trouble that we have reaching the result. So I will try to make a long story short. We start 10 years ago at the time of Gen 10 with observing with LBC at LBT 4 field around high redshift quasar and observing the field of this quasar with the 3 band, R, I, and zeta, in order to select the E dropout that their color suggests that they are at the same redshift of the central quasar. Among the 4 fields, J1030 was the most over dense, and so after all we concentrate on this field. The second step was to obtain near-infrared observation in the Y and J band in order to improve the quality of the selection, mainly rejecting the bright infrared object as a star and obtain a better and deeper selection down to redshift, down to magnitude zeta down to 25.7. The overdensity of this cleaning of the target was also confirmed with higher significance. And we were quite sure about the presence of the structure around the central quasar because the distribution of the candidate was highly asymmetric. you can see that the cross is the position of the QSO itself, and the circle are the candidate, and the angular correlation of the candidate was showing a positive signal compared to the green point that are the correlation of the rejected object. So, at the end, we have 22 robust galaxy candidates selected as I drop out, and we have to do the best, the more long step of the longer step of the work is to obtain a spectroscopic follow-up using a meter class telescope, because these objects are very faint. So we try and we do a lot of proposals. We obtain time at Keck and the Mauna Kea. The night of our observation, there was snow, but at the end, we observed 12 objects, and for 12 of these objects, we obtained a redshift, and for all the objects for which we obtained a redshift was all at redshift greater than 5.7, as expected by the I drop out. So no contaminant, no foreground contaminant. 4 of these Lyman break galaxies was confirmed to reside in the large-scale strata around the central QSO, and also we had 2 Lyman alpha meter discovered in an archival observation with Muse that is centered on the QSO itself. So at the end, we have 6 galaxies confirmed to live in the large-scale strata around the central QSO. This was the first spectroscopic identification of a galaxy over density around a supermassive black hole in the first billion years of the universe. In this slide, I show you the spectra, the optical spectra of this object, and that have been, the redshift have been measured thanks to the presence of a faint Lyman alpha emission that luckily avoid the gray band is the position of the strong skyline that affect the red part of the optical spectral range. As you can see from the histogram of distribution of the redshift of the object, the orange histogram, you can see and compare with the expected distribution of the redshift from the E dropout, the black dotted line, the presence of a peak of 6.3 redshift is quite unexpected, is of course not expected for a normal distribution of the E dropout. This allows us to confirm the presence of this large-scale strata with a significance level of 3.5, and the galaxy over density, no. There is a movie? Okay. No, it's not very important. It's just the galaxy over density is 2 times the background spectral density of object at this redshift, and this no, okay, no. It's just a movie of this image that's rotating, so. And so we confirmed the presence. This is important because the fact that this giant grow in an overdense ambient is expected by a lot of theories. So this was the first overdensity identified around a supermassive black hole redshift greater than 6. But how many other objects like this are or observed in today? So the main competitor to J1030 is this object, the J0910, that is an object, a redshift, is a quasar at redshift 6.6, that thanks to narrowband imaging obtained at the Subaru telescope that has centered at the Lyman alpha position of this redshift, they got a lot of Lyman alpha meter, the black point around in the figure, And also they have a confirmation of 6 objects by the detection of the C2 line with ALMA. And they also got a JWST proposal. The only other system at this redshift with the spectroscopic confirmation is SDSS J0836, that is a radio quasar redshift 5.8 that are 2 spectroscopically confirmed Lyman-Bray galaxy in a very small field of view. The image is a HST image. So in this case, the LBGs, in our case, the LBGs are far from the quasar, and in this case, we are just in the very inner part. Okay, the other 2 objects we have a suspect presence of overdensity around the quasar, Viking and the blazar that Silvia talked just before, but they don't have still the spectroscopic confirmation. On the other side, so this is all, 2 objects, 3 objects, and 2 suspected objects. On the other side, there is quite a number of structures that have already a confirmation. The black objects are the objects with the spectroscopic confirmation. They already observe a number of structures are actually greater than 6 that don't have a break between their members. And so, what is I try to give you some maybe confusing message. So it's clear that the observational evidence of the ubiquitous presence of large-scale structure around the redshift 6 QSOs is still debated. And there is also some large-scale structure without any sign of luminous QSO. But it's true that maybe the QSO is there, but we don't see it because there is obscuration or variability or what else. It's clear, and our experience on J1030 teaches us that it's difficult to find this kind of object. Moreover, the central QSO could affect this galaxy formation. So, further, of course, more statistics is needed and more observation is needed. It's not a new thing. So we need to increase the number of studied fields that are actually greater than, say, 6, and probably the radio QSO are the better candidate. Just 2 or 4 of the objects that I showed that have a structure around are radio objects. Fabio already got similar data with LBC around the J1641 object. I know that there is a proposal with LBC to observe the 2 luminous Hyperion quasar, and there is a proposal to obtain the spectroscopy on the blazer of Silvia. And finally, JWST will have a JTO proposal on 6 quasar redshift greater than 6 with NIRCam to observe the oxygen tree line in the companion object. And of course, another strategy is to improve the knowledge of the few LS around the redshift 6 QSO, and of course, J1030 is the best candidate to do that. We already obtained ALMA observation to detect the carbon-2 line, and the observation just started 3 days ago, and we have a proposal to going deeper in the optical to increase the number of candidates and collect and measure the spatial distribution, clustering level, and luminosity function of this structure. And finally, it's useful to compare these results that are not made by 5, 6, 3 objects with the theory simulation. I thank you for the attention. I leave you a warning.
Thanks a lot, Marco. So, questions?
And Marco, you said that the overdensity is a factor 2, and this is consistent with the models, or models expect more, less?
It's true that the overdensity is a factor 2, but is over a very large volume of 800 megaparsec. And but it's true that it's difficult to make a comparison with just few objects, because we don't know if we just pick the tip of the iceberg of this population, if maybe the concentration is more in the center of the field or far away. So the number is just a first hint of the overdensity, but a comparison is still difficult to do with this small number. For example, the radio quasar of Verzier, they got one very luminous object nearby the quasar. So in this case, there are two massive objects, and there are two probably dark matter halo very clustered. In this case, probably there is some possibility to make a comparison with the theories. In our case, it's just a first step, I think.
Any other questions?
Thank you. Thank you. Okay, sorry. Very nice talk. I have just a curiosity, actually. Why do you want to do the follow-up even for faint sources like J1030? I mean, you want to do the luminosity function, but then there are other motivations to do that? I don't know if... Okay.
Other field, you mean it's better to increase the number? You mean it's better to go in other field, or?
The question is why you want to detect not only the more brightest things but also the faintest?
Because first of all, you can better understand the geometrical of the. Moreover, is the luminosity function that will be very useful to compare with the simulation, because there is some simulation that propose that the presence of the central QSO will pump up the star formation, and so we will have a luminosity function that is more flat than the background. But with 6 objects, it's difficult. We know that the structure is there in J1030, so for us, it's a better place to go deep, because we know that there is something there. But it's useful for doing mainly comparison with the theory.
Any other questions? So let's thank Marco again. So it's now time for the flash presentations of the poster, and I guess Emanuele is going to call, no? I mean, the people can just come here. I wish to thank in the meantime all the speakers of the session, because they've been extremely sharp, all within the 15 minutes, so thanks a lot. Okay, so the order?
Yes, okay, so we have Luca Foffano, Izzy Garland, Vittoria Elvezia Gianolli, Ana Jimenez, Ivan Lopez, Matteo Nurisso, Alessandro Feca, and Luca Higuina. The same rules as yesterday, 2 minutes sharp, and the slides will change automatically. Present yourself in case when you start.
Good morning. My name is Luca Foffana, and I work as a postdoc at IAPS in Rome. Today we'll talk about absorption features in gamma ray spectra of BLAC objects. That is a work that we have recently published on a PJ. As you know, in BLAC objects, the optical spectrum is usually dominated by the non-thermal continuum, so the standard method to identify, so we need indirect method, alternative methods. For this reason, we thought about this new indirect method that may unveil the presence of some larger scale structures in this kind of object. And our idea is basically based on the trajectory of the jet. So the jet may pass through these large-scale structures, may enlighten them, and produce seed photon fields by reflection. And the gamma rays of the jet may interact with some of these seed photon fields and interact via gamma-gamma pair production. This means that the gamma ray flux would be reduced at certain energies, and you can see it in the second figure, producing some absorption features. The strength of these absorption features is related to the physical properties of these seed photon fields and large-scale structure, and specifically depending on the size and the photon density. And in this work, we applied this on the real data of a new extreme blazar recently discovered by the MAGIC collaboration, and the result is compatible with the values, reasonable values of, for example, narrow-line region. Thank you.
Hiya, I'm Izzy Garland, a third-year PhD student at Lancaster University, working with Dr. Brooke Simmons to understand AGN fueling in the absence of major mergers. In particular, my work looks at the effects of large-scale galactic bars on the presence of an AGN, or lack thereof. So, I'm working with a sample of 65 disk-dominated AGN, i.e. merger-free. We have Lick-long slit spectra for all of them, and Hubble images for about half of them. I'm showing some of those images on the screen now. The observed regions that we got with Lick are bounded by the red lines, and you can see the clear morphology in the Hubble images. So the first thing I did was reduce the raw data and then use just a standard SciPy code to fit the spectra, focusing in particular on the H-alpha emission lines, or the H-alpha N2 complex, so that we could use the H-alpha to obtain the star formation rate after having removed the luminous AGN component. I then worked using Sloan colours to get the stellar mass. However, this was a bit of a challenge because Sloan uses fibre spectra, which meant that the AGN was really in the way of getting these stellar masses. So we used HST images and GalFit to obtain the ratio of the disk flux to the total flux coming from the galaxy, and applied that ratio to the Sloan colours. Please speak to me if you want to know more about that. It deserves a whole talk on itself. So we've now got star formation rate and stellar masses, and we use these to select a comparison inactive sample of disk galaxies with the same star formation rate and stellar mass distributions. And it turns out that once you've controlled for star formation rate and stellar mass, the effects of bars are not actually that significant. Please come and speak to me if you'd like to know more about my work. Thank you very much.
Good morning, I'm Vittoria Vezza-Giannolli, a first-year PhD student at the universities of Grenoble Alpes and Roma Tre. I'm working with Piero Oliver Petrucci and Stefano Bianchi on GeoN winds. In particular, on ultra-fast outflows, UFOs are highly ionized gas that is flowing from the inner part of the AGN and are thought to play a major role in the coevolution between the AGN and the host galaxies. They are characterized by 3 parameters that are shown in the slide, so the outflow velocity, the ionization parameter, and the column density. What I'm doing is a statistical study between a GN sample, the subway sample that has been presented by Gabi the other day, that is composed of 22 quasars, and I made a comparison with the sample studied by Tom Besi of 42 Cepheid galaxies, and these 2 samples can be divided into 2 main subgroups, the AGN with that are hosting UFOs and those without. We are considering all the main physical parameters of the AGN and the ultra-fast outflows, and right now we are running an extensive correlation analysis between all of them. And about the results, well, a few spoilers in the poster, and then please wait for the paper that is in preparation. Thank you.
Hi everyone, I'm Ana Jiménez Gallardo and I work as a PhD at the University of Torino. Here I would like to present to you the work that my collaborators and I were carrying out to improve our understanding of ionized gas in radio galaxies. So with this work, I carried out Chandra-Muse comparisons to characterize both the optical spectral emission of the ionized gas and also the X-ray emission of the gas co-spatial with the ionized gas. In particular, I focus on two radio galaxies, both showing clear signs of feedback processes. So in the case of 3C318.1, what we found was the presence of an ionized gas filament co-spatial with an X-ray enhancement, which could be due to a lot of factors like photoionization, collisional ionization, etc. But more importantly, we found in 3C196.1 a possible first case of ionized gas filling an X-ray cavity. So if you want to know more about it, or whether it's possible or not, let me know. I will also present some preliminary results on a larger sample of radio galaxies, which could yield some clues on the high and low excitation dichotomy for radio galaxies. So come by if you want to know more. Thank you.
Well, hi everyone. I hope you are having a nice conference. My name is Ivan Lopez. I am a second-year PhD student in Bologna, working with Marcella Brusa and Silvia Bonoli, and we are trying to obtain an unbiased distribution of accretion ratios. Because this is very short and I have only 2 minutes, I didn't put any results here of the poster, but I put some questions just to turn on your curiosity in the project. These questions can be, for example, what is mini-JPAS? That is our survey that we are working, and why it has 54 narrowband filters. How are we doing to obtain the physical parameters of the galaxy host and also of the EGN? Where are the expected relation of these parameters, like, for example, the scaling relation between the mass of the black hole and the mass, the stellar mass of the galaxy. And spoiler alert, we are working until redshift 2.5, so our plots show a lot of scatter, but in any case, an easy forwarding model of each source up to redshift 0 can explain a lot of this scatter and also show distribution that they are similar to the ones in the local universe. So if you are interested in one or more of these questions, you can go and read the poster, and if I am close, you can ask for an exclusive tour guide of the poster. Thank you.
Hi everyone, I am Matteo from SISSA in Trieste, and I want to speak about this work that we are now doing about implementation of the magnetic reconnection phenomenon in simulation of jets and large-scale simulation. So the idea is that we want to study magnetic reconnection, but as we saw the other day with the nice talk by Eleonora Puzzoni, it's a phenomenon that is happening in microscopic scale. So the idea of implementing in large-scale simulation is difficult. So what we want to do, and what we did with our work, is to basically understand what are the important parameters that the plasma, the surrounding plasma, has to have around the reconnecting region, how to sample these parameters, and more specifically also how to identify the region in which the reconnection is happening in these simulations. So the idea is that we are interested in constructing the final spectra of accelerated particles, and the idea is that with an identification method and the sampling method of these quantities, we can follow the particles that are entering this region and do an update of the spectra, then following how the spectra evolves during the simulations. So what we see in the plot in the right is an example of a slice of a 3D simulation of a plasma column. The idea is to study an environment with an initial magnetic field with an helicoidal structure with current-driven instabilities, see how this simulation evolve, and to check if there is a behavior of the reconnecting region, what are the values, if they are interesting for particle acceleration. And what we can see in this example is that the distribution of the two main parameters that are important for the acceleration, they show a narrow distribution with the values that are interesting for particle acceleration. So we are looking forward also to fully implement the spectra update and study in details how many particles, where, and all the details about this simulation. So thank you.
Hi,
I'm Alessandro Peca, University of Miami, third year PhD student, and my boss is Nico Cappelluti. So a few years ago, I was working on my master thesis in Bologna, and we were working on faint X-ray sources, and sometimes you cannot have enough information. So we decided to check the multi-wavelength coverage, I mean photometry, in the optical and the infrared. And I was like, we have too many catalogs, too many formats, we have AB magnitudes, Vega magnitudes, then we have to match X-ray counterparts. So I was like, oh my God, sorry, this is a mess. This is the answer. So we put together 7.5 million AGN. This means that if an AGN is published in the literature, we have it. We have it, and we match all the AGNs together with a powerful machine learning algorithm using Bayesian statistics and also priors on the magnitudes. We have 66 wave bands from the radio to the X-rays, and everything is converted for you. So same units for everything. Also, we have a lot of redshift, and we have solid classifications. So current project, Also, we have already implemented Cigale, which is an SED fitting code, and everything is automated. So if you want a SED, we have it. Current projects, we have a web query interface. We are going to perform X-space spectral analysis and SED fitting over the entire catalog. Then we want to build multi-band and holometric luminosity functions, and we are going to work also on possible AGN misclassifications. So if you need an AGN, we have it. Just ask. Thank you.
Hi, everyone. As you might remember me from yesterday's flash presentation, my name is Luca Ghina. I'm a PhD student at the Brera Observatory in Milano, and this is my second poster. In particular, in this poster, I tried to summarize the results that we obtained in two recent studies that I've led, in which we were trying to address two quite different questions, but which actually might have the same solution. In particular, on the one side, the recent studies of the blazar population found that the space density evolution of these sources is significantly different if we look at them in the radio band or in the X-ray band. And then the other problem is related to the X-ray emission that we observe in some relativistic jets, many kiloparsecs away from the central supermassive black hole, and so well beyond any other AGN component. And as I mentioned, we argue that these two problems have the same solution, which can be ascribed to the interaction of the electrons within the relativistic jets with the cosmic microwave background photons. And in particular, we claim our results are based on the largest complete samples of blazars currently available, up to redshift 5.5, and also on the detailed study of the highest redshift jet results both in the X-rays and also in the radio band. Yeah, that's all.
Okay, so we are done for the session, and thanks for choosing our outline, and you can leave the room. Sorry. We reconvene at 2:45. Okay, thank you very much. Good lunch.
Scusa, aspetta. Yes.
Prendi le miglia con la compagnia nostra. C'è il volo gratis, 4 miglia.